Well, good morning. This is Tuesday morning, the 11th of July, 2017, 8:04, I believe it was, in the morning. A little bit late getting started, but sorry about that. I've been taking care of some other business. But it's supposed to be Math 238, differential equations course, but I'm the only one in the classroom. So hopefully the students will be coming in, but I will go on and get started where we left off last time. I was trying to think if there's any major announcements you need to know. I will tell you this one thing, it really doesn't affect anything unless you're looking for me while I'm in class today, but I am taking my physical science class on a field trip to Sanford Planetarium at the Christenberry Planetarium, Sanford University campus, and we are leaving at 12, which is when class usually begins, and we'll be back around 2:45, I hope, which is still during class time, and class will end about 3:30, as it normally does. So it really doesn't mess with my office hours, but if you're trying to find me today between 12 and 2:45, I will not be on campus. I will be with my physical science class at the planetarium at Sanford University. But I'll be back hopefully before class is over, and I'll be back in the office at 3:30, regular office hours. Where I got the biology interviews done yesterday. The dean sent us an email Sunday morning saying that we were interviewing yesterday. So I had very little notice of that, but at least it won't affect this class. But let me go on and say this. I know that next Tuesday, 1 week from today, I do have a doctor's appointment at 8:40, I believe it is, in the morning, but I have to be there by 7:40 for labs, and that means I won't be here in class at 8 o'clock. So I don't think, since the appointment's 8:40, I don't think I'll be out of there much before 9 o'clock, and then it takes me about 45 minutes to get from the clinic back here. So it'll be 9:45 before I arrive on campus at the earliest, okay? So the class ends at 9:50. So basically, next Tuesday's class will not be meeting here on campus. Now, I do have, and I think I've notified you of this before, and if you've been looking at the YouTube videos, you notice that the YouTube videos that I'm doing this term are at the end of another string of videos, okay? The earlier videos were ones I did last term or term before or whenever. So you can always follow where we leave off today or Thursday. You can then follow what would come next on the videos that I did last term and or the term before. But that being said, no class next Tuesday. I'll try to remind the students as they come in. But other than that, I hope not to have many more. I do know they have some sort of hearing going on. Can't think what they call planning hearing going on. Then I think the following week, and it's if my memory's right, it's either a Tuesday or a Thursday. And I know that it will interfere with either my morning class or my afternoon class. I just don't remember which. I think it's the morning class. So we may have another day I don't have class in. I am so sorry about this, but the administrators don't have any regard at all for classes. They just call meetings whenever they want to call them at their convenience, not at the instructor's convenience. So I'm sorry about that. Now, my doctor's appointment, I feel like I should do something about that. So we'll talk about that as soon as anybody shows up. And what we can do is, since I will be back here at 10 o'clock, by 10 o'clock, probably earlier, we can go on and make up that class immediately after that if either one of you can make it. If you can't, then we'll maybe find another time, say after 3:30 some afternoon, after I've finished with those classes. But if not that, then maybe just rely on the videos that are out there from previous terms. So I want to make up that one because that one's, I figure, is on me, not on the college. But the others, I don't know if we'll have a chance to make up. But anyway, enough said there. All right. We were doing section 2.5. Chapter 2 is first order differential equations. 2.5 is solutions by substitutions. And we had talked about this kind of stuff. Now we get to actually do it. And we have also introduced a new type of linear, of first order, not linear, first order differential equations, and this was the homogeneous equations. And again, what homogeneous equations is, let me put it somewhat simply, or I'll try to anyway. When you write the equation in basically differential form, okay, it doesn't have to be, it could be in another form as well. And now they give this definition, and it's absolutely true, but here's the bottom line to it. If when you write this differential equation in either differential form or other form, but usually differential form or something pretty close to it, and you look at the function, okay, especially if you write it in differential form, m of xy dx plus n of xy dy is equal to 0. Okay? Now, what do we mean for it to be homogeneous? If you look at your function, m of xy and n of xy, those two coefficient functions there of your differentials, and look at the degree of the terms in those functions, the total degree. You're combining the x's and the y's together, look at the total degree. And if the degree of every term in both m of xy and n of xy are identical, then that's a homogeneous function. Okay? Here's an example of this, example 1. Okay? Let me get my pen activated in the dark color. X squared plus y squared dx plus x squared minus xy dy is equal to 0. Okay? Now, first off, when I look at that, I say, is this an exact differential equation? Well, let's see. Let's take the partial of that first coefficient function, x squared plus y squared, with respect to y, and you get 2y. You take the partial of the second one with respect to x, and you get 2x minus y. No, that is not an exact differential equation. Even though it's in that form, it is not exact because it fails the test. But just a glance at this, and you notice the first term here is a degree 2. The second term here is degree 2. The first term here is degree 2. And the second term here, even though there's not an exponent of 2, this is degree 1, that's degree 1. They're multiplied together. You add the degrees, and sure enough, that's degree 2. This is a homogeneous differential equation. So we can follow the procedure that we did last time. I know it's been a while, but let's do that. And let's keep it a little simpler, okay? You see that those coefficients are homogeneous functions of the coefficient functions are homogeneous functions of degree 2. Every term is. And if we let y is equal u of x, that's going to u times x. That's going to be our fallback. Y is equal to u times x. Okay? Now, if we do that, the next step is what is dy? That's equal to, now, remember our, well, okay, du is u dx plus x du, okay? Just take the differential, I'm sorry, this is dy. dy is u dx plus x du, okay? Now, let's go back and do that substitution throughout the problem, okay? And this gives us x squared plus u squared x squared, that's your y, dx, nothing changes there, plus x squared minus x squared u, because y is ux and x is x. Okay, that'd be x times ux, would be x squared u, times u dx, because your dy is that, plus x du. Okay. Now, let's gather all the dx's together. Okay? This one would be x squared plus u squared x squared dx. Here we would have another plus x squared u dx. Okay, that's from this one times that one. And then we also have a minus x squared u squared dx. Okay, that's all your dx's, and your dy's would be simply, or fairly easily, plus x cubed du, I mean not dy, du's, du, minus x cubed u du. I think I did that right. Let's take a look at it. And by the way, this is equal to 0, and this should be equal to 0. Make sure we've got all of our terms in there correctly. Okay? Now, notice what we have here. By the way, we should put those in parentheses. Why in the world I did it that way, I'm not too sure. I took that first term inside here, but I didn't take the second term inside here. So, okay, there, I think I've got it. The x squared plus u squared x squared plus u squared u minus x squared u squared, all dx's, and then these, and why I didn't do this, I don't, let me clean this up some too. Okay, no reason to have that. Where my brain was, I sort of started writing and wasn't thinking. Okay, I think we got it. Okay, so we have x squared plus u squared x squared plus x squared u minus x squared u squared. Hey, those two add to 0. Plus x cubed minus x cubed u du. All these are dx, there's a du. Okay? Now, I guess maybe a little bit surprisingly, this is no more homogeneous. Okay? But that's okay, because what is it? This would be, in this term, we have x squared times 1 plus u dx plus x cubed. I don't think I need the parentheses there. I might. It might be helpful to have it there. Times 1 minus u du is equal to 0. Okay? Guess what that smacks of? Separable variables. Okay? Separation of variables. Let's see if indeed we can. And I really like to write that I think I may have a student here. All right. Good to see you. I get tired of talking to myself. So, let's see. Today's the 11th, right? Good deal. Thank you. Another paper in. I think that may be Yes, the first one for this course. So, thank you very much. And we've got here, get on the right date, the right line. Okay, let me pause for a moment here, turn on my projector, flip the lights. Not yet. Well, it's coming. There it comes. All right. I did want to let you know a couple of things. I announced it earlier, but since you're here, I don't know for sure if you can go back and listen to the very first part of the class. So let me say this now. I think last week I warned you and that we might lose a class because of interviews for biology position. No, not going to happen. Sunday morning, the dean emailed everybody on the committee saying that the interviews would be yesterday. So I had no preparation at all for when that would be. I didn't think it would be Monday. I hoped it wouldn't be Monday. So I missed 2 calculus classes and 1 physics class Monday. Miserable, okay? And one of those, the physics class, one of them was 22 students enrolled in that. Calculus class, I feel like 11 or 12 in that, and then the other calculus class, like 7 or 8 in that. So a bunch of students, no class. I was able to meet my smaller physics class last night, so we met, okay? But the interviews are over, so through with that, okay? Now comes the next interference. Now this one's on me, sorry about this. But I have a doctor's appointment. I think I told you earlier in the term. My hematologist only sees patients on Tuesday mornings. Only. There's no other time I can schedule an appointment with him. And he scheduled me for next Tuesday, 1 week from today, at 8:40 in the morning. But I have to be there for labs by 7:40 in the morning. So there's no way I'll be here for an 8 o'clock class. And that appointment being 8:40, I don't think there's any way I'll be out of there before 9 o'clock, and it takes me between 30 and 45 minutes to get back to campus, so I may not be back here at the earliest before 9:45, and the class only has 5 more minutes. Yeah, so class will not meet next Tuesday here. However, have you been to YouTube yet? Okay, you have. If you'll notice in there, the top videos are all from previous terms. You may not have realized that, but they are. The very top bunch are from sections in Chapter 4. And then you'll get to some that were from, I think that was from fall term. Then you'll see some that were from last term. And I usually, once I do a section in this one, I'll wipe out the corresponding one there so you won't have so many multiples there. But the next group that start in Chapter 2, they are from last term. And then finally you'll get down to this term, which started in Chapter 1, you know, with the syllabus and all that kind of stuff. Okay, so wherever we end up Thursday in this class, you can pick up the video from approximately where it was last term and watch that video. There may be a little bit of overlap. Hopefully there won't be many gaps, but there may be a little bit of overlap. Now keep in mind, that class was an hour and 15 minutes. Ours is an hour and 50 minutes. So you might need to, and it may not start at the beginning of that one, so you may have to scroll down to find out where we ended off here, watch the rest of that video, and then maybe part or all of the next video. So if you'll do that, I think that will move us along a little faster. Okay, so, or here's the other possibility. I have a feeling this won't work for you too well because you usually have to leave before this class is over. I should be back here before 10 o'clock. And if I am, we could meet from 10 to 11:50 if you'd like. I certainly can do that, but you can't, can you? Okay. I don't know if Megan can or not. If she can, I may do that, and then you'll actually have the current video out there, okay? But she's not here to ask, so I don't know. Another possibility would be 3:30, because I have my physical science class gets out at 3:30, I could meet then, 3:30 until 5:20. Would that be a possibility either on a Tuesday or a Thursday? Not for you. Okay, it'll be up to Megan. If Megan, either 10 o'clock or 3:30 works better for her than just watching the other videos, then we'll go for that. Then there'll be a new video out there. If she comes in today, we'll discuss it. If she doesn't come in today and comes in Thursday, we'll discuss it then. And if not, we'll just go with it. Okay. Now, there is one more, and I don't have the exact thing. The week after next, we have what they call our planning hearings. And the planning hearings, I can't remember when they're scheduled for. It seems like it might be something like 9 or 10 o'clock on a Tuesday or a Thursday. I don't remember which. If it is, then I'll either miss all or part of that class as well. I'm so sorry. That's the college. They don't give us any choice. It's whatever is convenient for an administrator. And of course, they don't teach classes, so they don't even think about classes. Last thing in their mind, the classes. So they don't care at all if they interfere with classes. So I'll find out more upcoming for that. So anyway, sorry, there's probably going to be one definitely interrupted class. We might be able to make that one up. And the other interrupted class we'll just probably have to do with on old videos, so if you don't mind. Now, this was example 1 on page 73. Chapter 2 is first order differential equations, and 2.5 is solutions by substitution. And the type of equations we're dealing with here are homogeneous equations. And I said this before, but again, in case you missed, you don't go back and listen to it. They have that little rule in the book about putting t's in there and the t to the alphas and that kind of stuff. That's absolutely correct. But to me, it doesn't say much to me. Here's what I look for. If you write your differential equation in differential form, like we did for exact differentials, write it like that. Okay? But any other form will probably work too. Now look at the terms here. And look at the degree of the terms. Degree 2, degree 2. Those are the same. Good start. Degree 2. This is degree 1, add those together. That's degree 2. That's a homogeneous differential equation. Okay? Because for your m of xy and your n of xy, every term in them has the same degree. Okay? Now, they all don't have to be squares and stuff. It's something like this, but yeah. Now, what do we do with that? Well, when I would look at that, first thing I would do, I did earlier, say, well, wait a minute. Is this an exact differential equation? If it is, we know how to do that. Well, what's the test for an exact differential equation? Take the partial of this with respect to y, not x. What's the partial of this with respect to y? Second? Yeah, partial of this one with respect to y. Okay. You treat x as if it's a constant. The derivative of a constant is 0. This is your only variable. You're taking the partial with respect to y, that would be 2y. Okay? You do the partial of this with respect to x. And what do you get here? 2x minus y. Guess what? Those are not the same. So this is not an exact differential equation. So you can't use the thing that we did in the last section. But we have already noted this is a homogeneous. So here is your substitution you make. Let's let y equal ux. Okay? Y is equal to ux. Okay? That is your substitution. Then you do a dy here. And dy would be u dx plus x du. Product rule, right? Okay? Now what we do is plug in either this or this anywhere we see a y. So you get the x squared here. Here's a y. Y is ux, but you're squaring that, but u squared x squared. So that would be u squared x squared dx. Right? Okay? Here we have a plus x squared, no problem there, minus x times y. Well, this y is ux. Well, x times ux would be x squared u. So we have a minus x squared u. But then we have a dy, and instead of dy, we have to put u dx plus x du, right? Okay. Now, let's get all your dx's together. Well, here's an x squared plus u squared x squared. That's all dx. Then you have this. This times dx, so that would be x squared u plus x squared u. But then you also have a minus x squared u squared. Minus x squared u squared. Group all those together, those are your dx's. Now let's get all your du's together. Well, there aren't any du's here, so our only du's are here, and that will be x cubed minus x cubed u, close parentheses, du. Okay? Very good. Next thing to note, here we have a plus u squared x squared, there we have a minus u squared x squared. Fantastic, we've lost that term, those terms. Okay? What do we have left? This term has an x squared, so you can factor out the x squared and leave you 1 plus u here, right? Plus, that term disappeared. And here you can factor out an x cubed. And what do you have left? 1 minus u here, du, and that's equal to 0. Hey, I like to look at the looks of this because this looks like it's separable. Because all your variables are in their own factors. Okay, so let's get all the x's with the dx's. That means let's lose this one and divide by x cubed. Divide by x cubed. And over here, let's get the u's with the u's. So we'll divide this one out. 1 plus u, divide by 1 plus u. Okay? Now, 1 plus u's go out here, x cubes go out here. What we have here is dx over x, that's what you're left with, plus 1 minus u over 1 plus u du is equal to 0. Okay? Now, this is something easily integrable. Okay? Yeah, that's going to be log x. No problem there. This is not quite so easily integrable. Okay? And there's a couple ways you can approach it. Not really one any better than the other. What I'm real tempted to do is move it to the other side of the equation. They don't do it in the book. That's what I was looking at. I would prefer to do it that way, but they don't. Okay? So leaving it just for their sakes, what I'm going to do is a long division with it. Okay? The denominator, and I'm going to rewrite this as u plus 1. That's why I wanted to move it to the other side. It makes it a little easier to do. Divided into minus u plus 1. Okay? Your denominator into the numerator. This is long division, but rewriting it in descending order of your power, and that would be u plus 1 divided into minus u plus 1. Well, u will go into minus u minus 1 time. That would give you a minus u minus 1, and we change signs and add. You could subtract if you wanted to, but it seems like easier to me. These go to 0, and that gives you 2. Okay, so you get a minus 1 plus 2 over u plus 1. So let's rewrite this. Okay, now they wrote the u's in front of the x's. I'll do that too. I don't see any particular reason to, but you can. So this will be a minus 1 plus 2 over u plus 1 du plus dx over x is equal to 0. Okay, just rewriting that, and you see that's exactly what they got from the result of long division. That's not the only way you could do it, but since they did it that way, we'll do it. Okay, now I'm running out of room, so I need to go somewhere, probably the second line here, and start erasing some of that. Okay, now again, we've got our variables separated, so we can I think I can erase that too. I probably can erase this. I hope I don't. I'm going to rewrite that just in case I do need it. Y is equal to ux. Okay. I may need that. All right. Now we're going to integrate these two forms here. Okay. You can integrate 0 too, which I probably should do. Why not? Okay. Now, we have the variable separated. What's the integral of this? What's the integral of minus 1 du? Second? Antiderivative of minus 1 du. Second? Antiderivative of minus 1 du would just be minus u, right? Yeah. So if you take the derivative of minus u, you get minus 1, right? Okay, so that would be a minus u. Let's see if I have room to write it here. Minus u plus, how about the antiderivative of the second part? 2 over u plus 1 du. If you did that as its own integral, what would that be? Okay, 2 log, natural log, of absolute value u plus 1. Okay? How about the next term, that next integral? Plus log of x, absolute value x, I guess we should say. And what's that equal to? No. Huh? No. Some constant. Antiderivative of 0 is some constant, because you take the derivative of a constant, you get 0. There's your constant of integration, okay? Your parameter, okay? Now, that is a solution in u and x, but we want it back in y's, okay? So let's go back and plug that in. This will be, okay. So this leads to, this is why I said I needed this, u is equal to y over x, right? Okay, plug that in for u, so we got minus y over x plus, now I'm going to change that ever so slightly. I don't know if I need to, but I'm just going to write it as this, okay? Log of u plus 1 squared. Well, guess what? I don't need the absolute value bars anymore, because u plus 1, whatever that's positive or negative, when you square it, it's going to be positive, okay? Unless, of course, you can't be 0, okay? And we don't want to go around multiplying by 0 anyway, so we already know you can't be 0, okay? So this will be plus the natural log of, and your u is y over x plus 1 squared, okay? Plus natural log of x, and we will keep the absolute value there, is equal to some constant c. Now, I can think of just a couple of ways to maybe clean that up a little bit. Let's see how they leave it. Yeah, they do a little bit of mess with it, okay? Well, one thing they do, rather than making this a C, since you have logs in there, they make that constant log C, which is still a constant, right? Okay, so that's a constant. So this then becomes a log C up here too. And what you can do now is, or what I would do, I'm going to need another row to do it. So let me erase this row too. Okay, and I don't think we need the long division anymore, so let me get that out of the way because it's sort of messing up what I was looking at anyway. I got confused. I said, where's that square come from? But it wasn't. It was a 2. So, all right. For some reason, the pen's not taking. One thing I would do is multiply everything by x. So you get minus y plus log of, I'm going to rewrite this slightly too. I'm going to write this as y plus x over x squared. Do you buy that? Least common denominator between x and 1 is y over x and 1 is x. So that would be y over x plus 1 over x. I'm sorry, but plus x over x, that's 1. Written this way, that would be y plus x over x, that's squared. Okay. I think that's okay to do. But I was multiplying both by x too, so that x is in front of the y, plus x log x, okay, I'll keep that in absolute value, is equal to x times the log of c. Now, I may be doing this in a pretty lousy order. Yeah, I probably shouldn't have done that multiplying yet. So let me go on and take that back out. Put the x over here, because I don't need that confusing the issue here yet. It will later, but not yet. Okay. So what I'm going to do now, well, all right. Perfect attendance. Good to see. Okay. But I'm going to need to do a little timeout here to go back and repeat something I've already said before Marcus got here, and then I said after he got here, and now I said after you got here. First and foremost, I think I told you last week that there could be biology interviews coming up sometime soon. The dean sent an email Sunday morning saying they were Monday morning. So we've already had them. So nothing to worry about there. We will not lose a class because of biology interviews. Okay. So I spent all day yesterday, or at least 7:30 in the morning until close to 5 o'clock yesterday afternoon, doing biology interviews and getting all those wrapped up. We got them done. They're done. History. Done for. Came back and taught my 5:30 class last night, so got that done. Okay. I forgot to tell Marcus this, but in case you're looking for me this afternoon, normally I'm in physical science class from 12 to 3:30, so I don't really expect any students to be looking for me, but sometimes they come by looking for me anyway. Just wanted to let you know, we're leaving campus right as soon after 12 as we can, going to Christenberry Planetarium and Samford University campus to the planet, to see a show at the planetarium. The physical science classes a little while ago finished the 3 chapter units on astronomy, and so they're going to go to the planetarium. That's a field trip. So I will be gone from approximately 12 o'clock till about 2:45. I'll be back on campus hopefully around 2:45 to 3, and then we'll finish the class till 3:30. Then I'll be in the office. So it doesn't affect office hours at all. It's just I won't be on campus if you're looking for me from 12 to about 2:45. Okay? We'll have office hours after this class, 10 till 12, and then again from 3:30 till 5:15. I do have to leave again this evening at 5:15 on the nose because I've got a meeting that technically starts at 5:15, but I'm going to be late getting there in downtown Birmingham. So sorry about that. Okay. So except for that, the day's normal. Wednesday should be normal. Thursday should be normal. Well, maybe. We'll find that out. Next Tuesday, Monday should be normal. Next Tuesday, I have a doctor's appointment. I don't know if you remember at the first of the term, I told you my hematologist only sees patients on Tuesday morning. So I can't schedule that for Friday, which I'd like to do, or any other time when I don't have class. He only sees patients on Tuesday mornings. And they scheduled me this time for 8:40, which means my lab started at 7:40, okay? Which means I won't be here at 8 o'clock. I'll be in the lab, probably already gotten blood drawn, but waiting around for the doctor's appointment. So I should be out of the lab by then. But with the appointment being 8:40, the odds are the earliest I'll be through with that, and probably not this early, would be 9 o'clock. If I were to be through at 9 and left the Kirkland Clinic at 9 o'clock and drove here almost as fast as I could within the speed limit, I still couldn't get here much before 9:45. And then we'd have 5 minutes of class. So there is no class next Tuesday. We will have class on Thursday, but not Tuesday. Okay? That said, that one I feel like it's on me. It's not the school doing it. It's my doctor's appointment. I couldn't help it. We have a few options. I'd like to make that class up for you. Okay? Now, sometime either Tuesday or even this Thursday or possibly even today, we could go continue class from 10 until 11:50 and do that. Is that, Marcus said he can't do it because he's got another class or something that you can't be. So is 10 to 11:50 on any Tuesday or Thursday something you could do?
Not any Tuesday and Thursday, but I mean, I could stay today.
You could stay today. Okay, do you want to do that? Up to you. Okay, so what we'll do, we'll make up a class today, so you'll just have to listen to it on YouTube, and then, okay, that'll give me 5 minutes to eat lunch before we leave on our field trip, but that's fine. I can handle that.
I think I could do next Tuesday too.
Yeah, well, it almost the same difference. Another option would be 3:30 to 5:20. Would that work better for you, a Tuesday or a Thursday? Huh? That wouldn't work. So you want to do it today then? Okay. So what we'll do is just keep on track. Now, what we could do rather than that, we could do 10 to 11, say, and then on another Tuesday or Thursday, do 10 to 10:50. You want to break it into pieces like that? Okay, you want to do the first hour today? We could do 55 minutes, okay? And then when do you want to do the second one? Thursday or next Tuesday? Thursday? This coming Thursday. So we'll wipe that out this week. All right, good deal. And if you'll listen to it on YouTube, then you'll catch up anything. Okay, so that's what we'll do. We'll just keep on trucking until 10:55 today, and then we'll do the same thing on Thursday. Go from 8 till 10:55. Okay, and that way I'll have a chance to eat lunch. Thank you very much, and we can go. The lunch is not that important. You know, I've got plenty to spare, so I could live on it for a week or two, but I'd rather not. Okay, especially with today being the field trip, that would be. I'd hate to be there in the planetarium when they're putting on the show and my stomach going, yeah, but never mind. That was silly, wasn't it? Okay. Now this is going to be hard to go over everything that we've done here. This was the original problem. Okay, x squared plus y squared dx plus x squared minus xy dy is equal to 0. Okay? This is on page 73, example 1. Now, on first glance, I'd say, oh, that looks like it could be an exact differential, doesn't it? What's our test for an exact differential? of this with respect to y. What would that give you? 2y. And then you would do what? And what would that give you? Those are not the same, are they? So, no, it's not an exact differential. You cannot do an exact differential with this problem at all. Okay. Well, you might be able to go back and do a substitution. Not a good idea. The other thing to look for, though, is now to look at the m of x, y, and the n of x, y again, and look at the terms, the degree of the terms. Now, they have that little thing with putting alphas in there, t's in there, and that kind of stuff. To me, that's sort of awkward. Here's what you look for. Look at the degree of this term. 2. Degree of this term? 2. That's great. They're both the same degree. How about the degree of this term? 2. How about the degree of that term? 1 and 1. And so it's 2. So sure enough, this is a homogeneous differential equation. Okay? And since it is, then this is the substitution we use. Y is equal to ux. Now, I've erased the rest of it, so you're going to have to go back and listen to it or look at it in the book.
What page did you say?
This is on page 73, example 1. Okay? There were many more steps here that, because I don't have a limited space here, I've just cycled through. And we've got down to this point. You made that substitution, and when you plugged it in and separated the dx's from the du's, because you lost your dy's, first thing you do, of course, is if this is your y, then your dy is u dx plus x du. Product rule, right? And then you plug the y's and dy's in here, so this y becomes a u squared x squared. This becomes a minus x squared u, and this becomes a u dx plus x du. Then the next step was group together all your du's and your dx's, because you've lost your dy's. You've lost all your y's. And that's what you did next. And then you found out you could separate the variables. And because now you have differential equations in u's and x's only, you separated the variables and came up with this for your u's. We did long division, which I've erased, and that came up with this. You'll have to go back and review that. It's in the book also, because they skip a lot of steps too. Now, they got it to this form, and then we took y was equal to ux, u is equal to x over y. That's what we put in for the u now. So this would be minus y over x, okay, plus log of y over x plus 1, and I took the 2 and moved it over there, okay, and then had a log x, that was our differential here, your antiderivative, okay, and then your constant that we had here, since you had logs here, just go on and make that log c. That's still a constant, right? But just make it log c. And that's where we left off, and okay. I think I was just about to erase another line. So let's do so. Sorry about this. Whoa. I don't know why my eraser isn't working. There it is. Hopefully it is. Yeah. Yeah. Didn't want to work, but now it is. Okay. Okay. Let's get all those logs together, okay? Pile all the logs up here, okay? And here's how we're going to do that. We're going to move this to the other side and this one to this side. Get all the logs on one side and all the non-logs on the other side. And I'm going to sort of switch sides too, so we, in other words, move this over there, but then it becomes positive, but that's where I'm going to start with. So that'd be y over x is equal to, and now we have a log okay, this is a little tricky here, but hang with me. Okay, log of y plus x squared minus log of x squared. Okay, I hope you remember the rule for logarithms, that the log of a quotient is the difference in the logs. So it's the log of the numerator, y plus x squared, minus log of x squared. Okay? And then we'll do another minus, because we're moved, no, that's a plus, log of x, okay? And then we have a minus log c, okay? Just a constant, okay? Now, which I'd written over here. So let's write it again. Y over x is equal to, now I'm going to do one more thing, okay? This one I'm going to leave alone, but this one I'm going to write as minus 2 log x. Is that okay? And then we have another plus log x. So this winds up being log of x plus y. I swapped the order, but it's okay. X plus y squared minus log x. I really should go back and make that absolute value, but the book doesn't, so I'm not going to do it either. Yeah, it does. It does leave it, so I'll put that. And then we'll have a minus log c, whatever c is. Okay. Now, what we're going to do now is rewrite that as y over x. This is just basically doing lots with logs. Okay. The log of a difference is the log of the quotient, sort of the undo in what we just did. Same thing. Oh, let's group these together first and make this minus log x plus log c. Okay. And then group those together and make that minus log of cx. Okay? You can put the absolute values in there too. Because the log of a sum is the product of the log of the products. No, the sum of two logs is the log of the products. Okay. Now we move that to the denominator, and that would give us y over x is equal to log of x plus y squared over cx. That's a fairly simple way to write that. But there's an even better way. Okay? Let's multiply through by x, and you have y is equal to x times the log of x plus y squared over cx. Okay? Now, no, I'm sorry. I did it wrong. That is correct, but it's not helpful. Okay. It is correct, but it's not helpful. Okay, sorry. They did it the other way. Okay. You have a log on one side and something that's not a log on the other side, right? Let's do an e on both sides. E to e. Yeah. Right? So this would then produce e to the y over x is equal to, and the e's and the logs go out, and that gives you x plus y squared over cx. Okay? Okay? And then they multiply both sides by cx. I don't know why their answer is any better than mine. It's not. But x plus y squared is equal to cx e to the y over x. Okay. Again, I think the answer I came up with the other way is no more complicated than that, but that's how they leave it. And that, sure enough, is a solution of one parameter system. Okay. It says, although either of the indicated substitutions can be used for homogeneous equations, and what they're talking about here, if you go back to the bottom of the previous page, page 72, the very bottom of the page, you can either use y is equal to ux, like we did in this problem, or you could have used x is equal to vy if you had chosen to do it that way. Okay? It said, although either of those substitutions can be used for homogeneous equations, in practice we try x equal vy whenever the function m of xy is simpler than the function n of xy. Okay? You go back to these. Okay? If this one was a lot simpler than that one, then use your other one. X is equal to vy. But if they're about the same, use y is equal to ux. Okay, and both of those are fairly equivalent. Okay. Also, it could happen that after using one substitution, you may encounter integrals that are difficult or impossible to evaluate in closed form, and then try the other substitution and see if it comes out any better. Okay, so you got both of those to use. If your first choice gives you something that's impossible to deal with, try the other one. Okay, and if neither one of them do, then you may just have to leave it in integral form. All right, so that was homogeneous equations. Now we do another one. Okay, all right, to erase all this. Okay. All right. Here's another differential equation. dy dx plus p of x y. So far that's looking like what? Say again? Okay, that would be a linear differential equation. You use an integrating factor. That would be true if this was equal to some f of x. That would be exactly what you would do. But this equation isn't that. This is f of x, y to the n. Boo, hiss, okay? Yuck. It's no longer a linear differential equation because that y is next up with the x's, okay? You want the y here. You don't want a y over there. You want just functions of x, okay? You want this to be a coefficient of 1, which we've got. The p of x, you want the coefficient of your y to be only in terms of x. Fantastic. You got an f of x over there. Fantastic. Except you also got a y there you can't get rid of. If you tried to get rid of it, you no longer have the coefficient of 1 here. Well, this is called a Bernoulli form. This is Bernoulli's equation, where n is any real number. Any real number. That's not any integer, any real number. This could be y to the 3/5, the minus 14/16, or 7/8, or whatever, you know. Any real, it could be the square root of 3, okay? Any real number exponent there is going to be fine. You just don't want any complex numbers. No, okay? Just as long as it's real. Now, most of the time they're going to be integers, okay? But they don't have to. It can be positive, negative, fraction, decimal, rational, or irrational. Yes. A lot of time I see n, I think of it being an integer. In this case, it's not any real number. Okay, that is called a Bernoulli equation. Okay, Bernoulli's equation. Now, that gives you possibly another paper topic. By the way, the other half of the class turned in his paper today. Okay, so don't forget that. Okay, Bernoulli could be several paper topics because there was a whole family of Bernoullis. There were two brothers, Jacob and Johann, I think they were, both brilliant mathematicians and physicists. I think they fought like cats and dogs, but I'm not sure. They may have supported each other. I don't remember that. And at least one of them had at least one son, Daniel Bernoulli. It seems like they had other children. And they fought like cats and dogs. They were a fairly dysfunctional family. They were all so brilliant, and they competed with each other. One time there was a story of the father expecting to win this big prize in either physics or mathematics. He entered it. He usually won it without any problem. And he didn't know that his son decided he would enter it that year, and the son beat the dad for the prize, and the dad kicked him out of the house. Okay, so, they were a rather strange crew. So any or one or the whole family or whatever would be a good paper topic. How did whichever Bernoulli it was come up with this equation? There are many other principles and other things that are attributed to one or another of the Bernoullis. There's a lot of potential paper topics just within that family. Okay, either about the people or about the things they came up with, either mathematically or physics. Okay. Now, of course, if n is equal to 0, then y to the 0 is 1. You don't have a y over there. That's a linear differential equation. Okay? But even if n is equal to 1, then that's a linear differential equation. It's just not the kind we usually like to have. But if n was equal to 1, then that would be a y there and a y there. And then you could have divide through by y, that gives you a 1 over y here, and you would have everything else in terms of x's there, and that would be simple. So if n was a 0, you have your standard old linear with an integrating factor. Okay, that was not that great to do, but pretty easy, straightforward. If n was equal to 1, then you just have a separable equation. So those two cases, yeah, you can do them real easily. But if n is anything other than 0 or 1, then you have a Bernoulli equation. Okay. Now, so what do we do with that? Here's the substitution we use then. If n is anything other than 0 or 1, we do this one. Y, or u, is equal to y to the 1 minus n. Okay? Of course, now, again, this is as long as n is not 0 and it's not 1. N is not equal to 0 or 1. Anything else, that works. If it's equal to 0 or 1, don't even mess with this. Go on and solve the equation by linear fashion. Okay? Now let's see what we get. If that's your u, then let's do du dx is equal to 1 minus n times y to the minus n dy dx. Right? And then your dy dx is equal to y to the n over 1 minus n. I say n and write 5? Where did that come from? I don't know. Okay. Du dx. Okay, so plug that in here. Y to the n over 1 minus n plus p of x times, that's just a function of x, so don't worry about that, let's get this and say, write this another way, y is equal to u to the n minus 1. Do you agree with that? If u is equal to y to the 1 minus n, then divide both. No, that may not be correct. No, I don't think it is. Let me take on that just a minute. Okay. Let's see. If u is equal to y times y to the minus 1 n, that's the same thing. Y to the 1 times y to the that. Then I don't know. So I don't waste too much time on that. Whoa. Huh. All they say, it reduces to a linear equation without showing you what that linear equation is. Actually, it's far easier to do with numbers in there than the letters. So let's go to example 2. I thought they were going to do it analytically. They're not. Let's just go to example 2. So let's erase all this, and we'll see if we're heading in the right direction. Okay. All right. Here's your equation. X dy dx plus y is equal to x squared y squared. Okay? Now, the first thing you ask yourself, you say, self? No. Is this in any kind of standard form? Say again? I can't hear. Okay, it's not in differential form, and I'm not sure we even want it in differential form. We want it in sort of our standard linear form. Is that anywhere close to our standard linear form? Why not? Yeah, you got the x as a coefficient. So the first thing you got to do is divide that out. Okay? So we'll divide everything on both sides of the equation by x. Okay. All right. So now we have dy dx plus I'm going to rewrite this as x to the minus 1 y. Is that okay? Okay. Equal to x y squared. Okay? Now we have it in more of a standard form. There's your dy dx. There's your p of x, 1 over x, right? And there's your f of x, and then your y to the n. Now, again, this happens to be an integer. But the integer is neither 1 nor 0. Okay? So now let's do the substitution they suggested. The u is equal to y to the, what was it? Y to the 1 minus n. Remember? Go back that one page, y to the u is equal to y to the 1 minus n. N here was 2, so that'd be 1 minus 2, so u is equal to y to the minus 1. There's your substitution. All right? Now, let's proceed with that substitution. If that's the case, then du is equal to minus what? Y to the, no, you're taking derivative, minus 1 dy, right? Okay. Now, that also means, let's see, which way do I want to go on this? I think we want to write this as dy, I hope I'm not skipping too many steps here, du. What I'm doing is dividing by du, or writing that in differential, out of differential form this way, but that would then be a minus y squared. Do you see that? In other words, what I'm doing is moving this to the other side. Maybe it's plus y squared. Basically, dividing, we're not doing it, but dividing by du, and then multiplying by y to the second, and then doing minus sign also. So I think that's correct. Okay? So that's what dy du is. Okay? I'm not absolutely certain what I want to do, but let's proceed with it. What we have now is dy dx is dy du times du dx, which we haven't even introduced yet, plus x to the minus 1 y, oops, yuck. The other implication here is that then y is equal to u to the minus 1, right? Okay. So rather than y, we write this as x to the minus 1, yuck. X to the minus 1, u to the minus 1, and that's equal to x times u to the minus 2. Okay, but this dy du is equal to minus y squared. So what we have now is minus y squared du dx plus x to the minus, no. We don't want the y squared in there. Let's get that in terms of u. That would be minus u to the minus 2, because y is u to the minus 1, so y squared would be u to the minus 2. So correct that. Be minus u to the minus 2 du dx, okay, plus x to the minus 1 u to the minus 1 equal x u to the minus 2. Now, let's multiply by a minus u squared. That goes away. You get du dx plus minus So as you multiply them by minus u squared, that be x to the minus 1 u equal a minus x. Now that's a linear differential equation, okay? Okay. Make sure we wound up the same place they did. All right. What's that? Okay. Sure. I'm going to keep. In fact, I think I'll take a little break while you're gone because I need to. I've got one. I'm going to have it soon anyway, so I'm going to. Yeah. Yeah. All right. Let me pause this. Okay. Now, I may have proceeded a little bit differently from the way the book did, but we wound up at the same place. du dx minus 1 over x u, which is exactly what I've got here. I wrote it x to the minus 1 u, is equal to minus x. Now, this is a linear differential equation in using x rather than y's in x, and we can go back and use our linear rule for this, the substitute integrating factor, okay? And how did we get that integrating factor? Well, if you recall, you identify what is your p of x, so the p of x is equal to x to the minus 1. And what did we do with it? We integrated it, okay? So the integral of, actually I think it's probably better, dx over x is log x, okay? We don't need the plus c's or anything else. Then we raise this to the exponential, okay? And that would then be x, okay? So there's our integrating factor. So what we do with that is multiply that by both sides. X du dx minus u is equal to minus x squared. Okay? Well, this right-hand side, I think if you'll pay much attention to it, is indeed an exact differential of derivative with respect to x of ux. Okay? Let's just do it to see. That'd be x du dx minus u. Wait. Ooh. Minus sign there. I think what we wanted to do was make this a minus here. So this would then be a minus, and that would be a minus x then. Okay? All right, let me go back. Okay. What's that? Okay, yeah, either this place on either side, whichever you prefer. How long before it, I guess, but yes, that one's pretty convenient too. Before you long enough, you think you can see past me here. I'll try to stay out of your way, wherever you want to be. Okay.
Oh yeah, I can see.
Okay. All right. I had jumped out into solving this and realized I didn't quite have it in the form I needed. We wound up the same place they did. If you got, you're still getting it other than the when you get it open, you'll see they say du dx minus 1 over x du, it was here. Du dx minus 1 over xu is equal to minus x. Same thing we got. And then I went to do the integrating, I went to do p of x, and where I messed up is p of x should be minus x to the minus 1, not x to the minus 1. So, no, sorry. Okay, this is minus x to the minus 1. And then what we do with that is integrate that, and that would be minus derivative of that'd be minus log x, and you take e of that, and that would give you goodness gracious. Got myself sort of lost in the sauce here. That would be log of x to the minus 1, bringing that into the inside, and then that would be x to the minus 1, I think. I hope I haven't screwed that up. Okay, x to the minus 1. Okay. And that would then be, multiply that through, and you have x to the minus 1 minus x to the minus 2u, and that would then be equal to minus 1, I think. Okay. All right, let me see if I'm getting way screwed up here. Yeah. E to the minus, that would be x to the minus 1. And when you multiply that through, you get, let me erase this term down here because that was the way I did it the first time. Okay. You get x to the minus 1 du dx minus x to the minus 2u is equal to minus 1. Okay? Now, what is that? That should be a derivative of a product. And the product should be u x to the minus 1, or x to the minus 1u. Okay? Let's see if indeed that gives it to us. Derivative of a product would be I'm going to do the second times derivative of the first, yes, plus the first, u, times derivative of the second would be minus x to the minus 2. Yes, that is exactly correct. Okay? And this should be then equal to minus 1. And then if we do write it in differential form, this would be d of x to the minus 1 u. I'm writing it the other way now. I don't know why, but I just wrote it first that way. Is equal to minus dx. Integrate both sides of that, and you get x to the minus 1 u is equal to minus x plus c. There is where you introduce your constant. Okay? Now, let's go back here, and u is equal to y to the minus 1. So this would then produce x to the minus 1, and u is y to the minus 1 is equal to minus x plus your constant c. All right, so which way do we want to go here? Let's say let's multiply everything by y, and you get x to the minus 1 is equal to minus xy plus c. Well, let's do cy since we're multiplying by that. And then factor out the y, and you get y is equal to 1 over x times c minus x. If I did it right, I think that's what you turn out with. So they have a, well, yeah, we got the same thing, but for some reason they wrote it in a different form. They wrote it, they multiplied the x through, and they have y is equal to yeah, 1 over a minus x squared plus cx. Same thing I got. I like my form a lot better than theirs. I don't know why they chose to write it in that form, but yeah, that's what you get. So that was a Bernoulli equation. And just to get that, it didn't look like a Bernoulli's equation at first because it had a coefficient here. So when you divide by that coefficient, then you have a dy dx, good, coefficient 1. Some function of x times y, fantastic. And then you have some function of x, okay, but it has a y to a power other than 0 or 1. That makes it a Bernoulli form, okay? And how do we deal with that? Our substitution will then be u is equal to y to the 1 minus 2. As long as that's not a 1 or a 0, that works, okay? So that would be u is equal to y to the minus 1, which then, of course, means y is equal to u to the minus 1. And dy would be minus 2 u to the minus 2, well, yeah, that's how I should have done it. I should have done a dy at this point. The way I did it was really convoluted, but it still gave us the same answer. But if you did it this way, dy is equal to minus 2 minus u to the minus 2. Okay? So dy du is that. And so, yeah, minus u to the minus 2. Exactly what we got. A little bit worse getting there, but yeah. So then we take this differential equation and write the dy dx is dy du times du dx. Okay? Well, we know what dy du is. That. Okay? Plus x to the minus 1. Y is u to the minus 1 equal x, and y squared would then be u to the minus 2. Okay? But this right here, dy du is minus u squared, u to the minus 2. So this would be minus u to the minus 2 du dx plus x to the minus 1 u to the minus 1 is equal to x u to the minus 2. So we wrote that. Multiply both sides by minus u squared. So this will disappear. This becomes a minus x to the minus 1 u to the first power, and this becomes a minus x. U squared times the minus becomes minus, and u squared times u to the minus 2 goes to 1. Okay? now you have it in linear form, okay, with one problem. Okay? You have a minus sign here. And that's where I just about messed it. I got so far as I said, whoops, that's not right. You need that to be a plus. So that needs to be a plus of minus x. So your p of x is minus x to the minus 1. And then you integrate that, and that gives you minus x, log x. Okay? And that would be log of x to the minus 1. When you take e of that, you get x to the minus 1. And that's your integrating factor. So you multiply that through here, you get x to the minus 1 du dx minus x to the minus 2 u, and then minus x times x to the minus 1 would be minus 1. And then this is the perfect derivative equal to that. Integrate that, you get your x to the minus 1 u is equal to minus x, and then there's your process of integration. And then you proceed to get it into another form. Can't see where I did it, but you plug in the u is equal to y to the minus 1 then. So this will give you x to the minus 1, there it is, y to the minus 1 is equal to minus x plus c, which is exactly what we got. And then multiply the y over here, divide by this. So you would have y is equal to 1 over x times 1 over c minus x. And that's exactly what we got. And they wrote it, y is equal to 1 over minus x squared plus cx. Same deal. Okay. There's the substitution used to clear a Bernoulli form. And that works for any real number n. Again, it doesn't have to be an integer n, any real number n if you have y to the n, as long as that n is not 0 and it's not 1. If it's 0 or 1, it's going to solve the problem. You can do it. Okay, but it is, then yeah. Now, the one other that we're going to look at is reduction to a separation of variables. Okay? So we're going to go with a new form. All right, to erase this one? Okay. Here we've got our differential equation. dy dx is equal to some function of ax plus by plus c. Okay? Now, I'm trying to think why they want to use capital A, B, and C there rather than lowercase a, b, and c, and I can't think of a good reason. There may be one, but I can't think of it right now. Okay? Now, that doesn't really look like any form we've had so far, in my mind. Okay? So, here's a substitution that may make it look like some form that we're more used to. Okay? Their substitution is let u equal the innermost part of the function here, ax plus by plus c. Okay? Now, usually the next step was then du is equal to a dx plus b, I hate to mix things like this, y let me write it this way. du dx is equal to a, we won't even put the dx in there. Oh, yuck. No. Okay. Hit the wrong key. Okay. Okay. Plus b dy dx. Yeah. Leave it there. The c goes away. Okay, let's recap what we're doing here. There's our substitution. Let u be the innermost part of that function. Okay? So then du would be a plus b dy dx. Du dx would be a plus b dy dx plus 0. Root of 0 is 0. Okay. Now, here's the caveat here. B cannot equal 0, okay? If B were equal to 0, we've got problems. And here's why. The very next step, then solve for dy dx, and you would have B times dy dx is equal to du dx minus a, and then divide both sides by b. That's why you can't have a b equals 0. Okay. Now, we're not going to proceed any more with this. Just that's going to be our approach. Let's make it a little simpler with real numbers, with a problem here, example 3. So I'm going to erase all this, but that's generally what we're going to do. So here's what we got. dy dx is equal to minus 2x plus y squared minus 7. Okay? And this happens to be an initial value problem. It didn't have to be, but they've made it one, where y of 0 is equal to 0. Okay. Okay. Looking at that, not a linear differential equation, not separable, not any other thing, okay? But if this thing right here were some other function, let's say our u, okay? So that's our substitution here. Let's try this. It's almost like what we did with substitutional integration, only then you only deal with one variable. Now we're introducing a third variable here. So here's our substitution. Let u equal the innermost part of the most complicated part there, minus 2x plus y. Okay? Then du, I'll write this as du dx is equal to minus 2 plus dy dx. Okay? Oh, and by the way, the b is not 0. No, the b is 1 here. What if the b were 0? Then that would just be a function of x. You wouldn't have a problem. That would not be an issue. So for this to be an issue, the b can't be 0. Okay? So it's not like we have to really avoid it. If it was 0, your problem is much easier than what you got now. Okay? Okay. The next step here is isolate dy dx. Well, that's pretty easy. dy dx is equal to 2 plus du dx. I don't know which side they put it on. I like to do it that way. Okay? Now let's plug and chug. This would be 2 plus du dx, right, is equal to let's solve this for y. This becomes y is equal to u plus 2x, right? Which, of course, that also would have given you dy dx is equal to 2 plus du dx. Yeah. So everything's looking good so far. So this will be a minus 2x plus u plus 2x squared. Huh, look at that. Okay? Minus 7. So this will be 2 plus du dx is equal to here, our plus 2x minus 2x add to 0, right? So that'll be u squared minus 7. Okay? Let's subtract 2 from both sides. And what we have is du dx is equal to u squared minus 9. What do you reckon we could do with that? How so? Write this in differential form. Du is equal to u squared minus 9 dx, right? Now let's separate the variables. Divide by u squared minus 9, divide by, I'm going to go on and factor that if it's okay, just save a step, u plus 3 times u minus 3. And these go away. You can integrate both sides, and just this one side gives you x. That's all it gives you. Okay? It's going to be x plus c. Trying to figure out whether it's better to put that in now or wait. I'd say let's wait just a little while. And let's deal with the other one. How can we do that integral? Nope. That's in the denominator. Partial fractions. Oh yeah, we thought we were through with those, weren't we? No. Those are just tools in our tool belt, okay? So how do we do this? Do you remember how that goes? We say we write that as a over u plus 3 plus b over u minus 3. And that's supposed to equal to 1 over u plus 3 times u minus 3. Now remember the little trick we did here? Okay, you pick a value for u which you would think it shouldn't be. No, it's simpler than that. Pick a value for u. That's good for any value for u. Except, of course, you would say u can't be equal to plus or minus 3. But that's actually what you choose. U equal, say, plus 3. If u is equal to plus 3, that goes, so let's write u is equal to 3, okay? Multiply, okay, I'm sorry. Should have multiplied first. Let's multiply both sides of this by u plus 3 times u minus 3. So that's going to wipe out there. So you just have a 1 over here, okay? Is equal to, and you multiply this by u plus 3, that times u minus 3, that will give you a times u minus 3. Okay, multiply that side by u plus 3 times u minus 3. The u minus 3's go out, so that gives u plus b times u plus 3. Okay? Now, you set u equal to 3. Well, this doesn't have any u's in it, so you just have a 1 there is equal to, but this goes to 0 now, doesn't it? And that will give you 6b, right? So that would indicate that b is equal to 1/6, okay? Now, it's pretty easy also to substitute in a u equal minus 3, and in that case, you still get a 1 here is equal to minus 6a, and that goes to 0. So a is equal to minus 1/6. Okay, we plug those into your integral, and this will be the integral of minus 1/6, the integral of du over u plus 3, plus 1/6 times the integral of du over u minus 3. Okay? And that's equal to x. Maybe, I think we can ought to put our plus c. I don't think it'll be in our way. We'll try it. Okay, what does the left-hand side give us? Minus 1/6 log of u plus 3 plus 1/6 log of absolute value u minus 3. And that's equal to x plus c. All right. The rest is just sort of manipulating numbers and stuff. I'm going to multiply both sides by 6. And that gives me, I'm going to reverse the order to log of x, or u minus 3 minus the log of u plus 3 is equal to 6. Now I'm regretting I put the c there. Oh! I think we're still okay. It's messy, but it's doable. I'm going to do it, carry it on. X plus c. Okay, just as if we're fine. These two, I'm going crazy here with my lack of space. This becomes log of u minus 3 over u plus 3 is equal to 6 times x plus c. Okay? Let's take the exponential of both sides. Now they're calling this C1, so let's go on and call it C1. We'll see why they do that in a minute. Let's take the exponential of both sides, and this gives you absolute value of u minus 3 over absolute value of u plus 3 is equal to exponential of 6x plus 6c but e to the 6c is in your other constant c. So I'm sorry if I'm skipping too many steps, but I just don't have much room. In fact, I've got to erase some stuff anyway. So let me go on and do that. Probably should have done it a while back. Okay, all this was taken care of. We've already done this, so nothing new here. Okay. And I don't think we need that either. I sure hope we don't. And I don't think we need this either. I'm going to leave that top line because that just indicates where we came from. I hope I haven't erased too much. Okay. So what we have here, when we do our exponential, and I'm afraid maybe I did erase too much because I don't see it now, but here's what we had. Absolute value u minus 3 over absolute value u plus 3 is equal to c e to the 6x. Okay. Now we plug in what u is. Or you are, I don't know. This would be minus 2x plus y minus 3 over minus 2x plus y plus 3 is equal to c e to the 6x. I wrote something down wrong. So y there, not a... yeah. Now, they did it a little differently, and let's see if there's any advantage to the way they did it. Looks like there could be. But I'm not seeing it right now. They solved, rather than plugging in for u, they solved for u. And I think either one of them do fine. Let's plug in our initial condition, y is equal, when x is 0, y is 0. So this would then produce, let's see if this works. When x is 0, y is 0, so that would give you negative 3 over positive 3 is equal to c is equal to c. So that would be c is equal to negative 1. And that's exactly what they got. Okay? Now, what you have is minus 2x plus y minus 3 over minus 2x plus y plus 3 is equal to minus e to the 6x. Can't read my writing here. So let me go back and clean that up a little bit. Okay. Now, that's hard to write y as explicit of x, but it can be done. They did it earlier, perhaps easier, but let's do it now. I'm going to clean some space here to do it. So, sorry, this is taking way longer than it should. Okay. Now, what we would have then is minus 2x plus y minus 3 is equal to minus 2x plus y plus 3 times e to the minus okay, e to the 6x, but because that was a minus there, that should change the sign of all these. So that'll make that a plus and make these two be minuses. That one and that one. Okay. Now, what they did in an earlier step, now I'm doing in this step. Let's get the terms minus 2x plus y minus 3 is equal to 2x e to the 6x minus y e to the 6x minus 3 e to the 6x. It's a little bizarre doing it that way. What we're going to do is get all the y terms together and the x terms together. So what we're going to do is add 2x to both sides. Okay. We're going to subtract 3 from both sides. No, add 3 to both sides, sorry. And that, now let's also add y e to the 6x to both sides. All right. Now what that gives us is a y times 1 minus the 1 plus e to the 6x. Okay? And that's equal to all right, I'm just going to write it out. Let me see. They factor out a 3. Let's see if we can. Oh, let's just write it out. That's equal to 2x e to the 6x minus 3 e to the 6x plus 2x plus 3. Okay. I'm really beginning to wish I had done the way they did. I probably erased too much there, but let's go from there. it's all algebra here, just, getting the terms to work. And I'm sorry this is taking me so long. I'm trying to keep an eye on what form they keep theirs in. Our form was perfectly fine. It just is a little messier than theirs, but I just wanted to rationalize it just to feel good about it. Oh, there it goes. I like to feel good. Okay. 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 So here's what they did, it looks like anyway. Factor out of 2x, and you have an e to the 6x plus 1. Plus 3 times, let's make that a minus 3. E to the 6x minus 1. Okay? Yeah. And then this is y times 1 plus e to the 6x, right? Okay. Divide both sides by 1 plus e to the 6x. Divide this by 1 plus e to the 6x. Divide this by, let's write it as e to the 6x. 6x plus 1, okay? Sorry, I'll change that in the middle of the go here. Probably should have done it all along. Here, this goes out. That's the same as that, so that goes out. So what we have is y is equal to 2x minus 3 times they do a plus 3. Got it. They do a plus 3 here, reversing the order of that, making it 1 minus e to the 6x over 1 plus e to the 6x. And that is the answer they got. Wow, what a pain. But, got the same thing. So, yeah, it's doable. Probably would have been easier if I had done it back when they did, but it works out either way. Homework exercises 2.5. Do any of the odds 1 through 13. Do either, 1 through 9, okay, and then do either 11 or 13. Then do any of the odds 15 to 21, no, 15 to 19, do 21. Then do any of the odds 23 to 27 and do 29. And then you can look at the discussion problems if you wish. However, I would look at them for this reason, because in number 35, that you really don't have to do, a differential equation of some other form is known as Riccati's formula. And it relates to Bernoulli's equation, and you can read on that. So you can write on who in the world was Riccati, or how did he develop this equation, or how does it relate to Bernoulli's, or that type of thing. There is another one here, number 38. It's talking about population growth, and it referring to an equation they call a logistic equation. What is your major, by the way? Chemical engineering. Okay, let me try to think. It seems like to me that some of your chemical reactions might follow a similar pattern to that one. I can't remember for sure if you use logistic equations in chemical formulas as well. My gut feeling is yes, you do, but I'm not absolutely certain about that. So you might run into a logistic equation somewhere or another. My wife is an epidemiologist, and diseases follow this. I mean, population growth follows it. But if you think, what is diseases? That's population of the disease. Yeah, you're following a disease population, okay? And it follows the same type pattern. In other words, it's sort of like the spread of bacteria or germs or things like this. It follows the same. So, anyway, that's the end of 2.5. Now we get to 2.6. Now, I hope this doesn't sound too discouraging, but everything we've done, separation of variables, linear equations, that's the integrating factors, exact equations, exact differentials, homogeneous equations, Bernoulli's equations, okay? All these you think, wow, we must have enough tools in our belt to solve any differential equation. No way, okay? Most of them are not going to be solvable no matter what technique you use. So in that case, we use a numerical method. And I think you'll see this was in your course description, numerical integration or numerical methods or something like that. This is probably all we're going to get time for, but we'll hint toward things that we probably won't have time for. Okay. And this almost goes back to what we did earlier when we were looking at the charts or graphs of differential equations, okay, using the tangent line. If we had a differential equation that was like this, y prime is equal to some function of x and y. And this function of x and y is not separable, it's not linear, it's not exact, can't be broken down in a Bernoulli's or homogeneous or any other form like this. It's just a real pain in the neck. But you also have your initial condition, y of some x0 is equal to some y0. Okay? Now, the first assumption is, even though you can't solve this in any of the techniques we've done so far, let's assume that, yeah, it is a real physical problem and you know it's got a real solution. You just don't know how to get to it. Okay? So let's assume that first order differential equation with this initial value does possess a solution. Okay? Now, that function f of xy is just some function of x and y. Okay? It may be a really nasty, ugly, miserable looking thing that you can't integrate or do anything else with, but it's just some function of x and y, right? So if it's just some function of x and y, you can pick a point, any point. Pick a point. 2, 3. Okay, plug in x equal 2, y is equal to 3 into that function f of xy, f of 2, 3. Evaluate what it is, and that gives you the derivative of the function at that point. Just like we did before, remember that? The derivative is the slope of a tangent line there. And you can pick other points. In fact, the point I would have chosen maybe was x0, y0. Okay? Plug that in, and you've got a derivative there, and then estimate other points. It looks like that's going to, and sure enough, you can come up with a pretty good representation of what your solution is. Okay? let's say we have this problem. Y prime is equal to 0.1 times the square root of y plus 0.4 x squared. And we know that y at 2 is equal to 4. Okay? Now, nonlinear differential equation, non-separable differential equation. So since it's nonlinear, you can't use the integrating factor. It certainly is going to be miserable to try to come up with a exact differential equation. I don't think it'll possibly work. It's a mess. It's a fairly simple looking thing, but it's a mess. Okay? Now, it cannot be solved directly using any of the methods considered 2.2, 2.3, 2.4, 2.5, anywhere along there. Okay? Now, we do know when x equal to y is equal to 4. So let's pick that as a point. Let's pick the point 2, 4. And let's see what y prime is there. Y prime at 2, 4, x equal 2, y is equal 4, okay, would be what? 0.1 times the square root of 4, so that would be times 2, plus 0.4 times 4, right? My eyes are going dry on me. I don't know why. Anyway, let's go. So the derivative, y prime at 2, 4, is equal to 0.01. No, I'm sorry. I thought that was squared. It's not. I can't read my writing. It's times 2, not raised to the second power. 0.2 plus 1.6, right? And that's equal to 1.8. All right. So at the point 2, 4, which you know is on the graph, okay, you know it's there, your derivative is 1.8, okay? So the slope there is 1.8. All right. Now, you got your book, you're looking at it, okay? You see the graph there, okay? Now you see that the solution curve that goes through there, we're estimating. But your derivative there is very close to that curve, really close to 2 and 4, the point 2, 4, okay? So what you would do is the process known as a linearization of the function value at from that point on, when x equal 2 and y is equal to 4. Okay. I may have to stop and get some water because I'm having trouble breathing now. What's that? Well, I hate to because we're got about 30 more minutes, but let me run and get some, okay?
Did you want me to write the answers in the blank?
It doesn't matter. If you got them on the other, I'll find them there. Okay. So we got the slope of the function, we have a point, and we have the slope at that point. Okay, now, okay. Or you've got your picture. I was trying to say if I was going to need to write that. Now, you see the figure, they have a figure 2.6.1, which shows the magnification of the neighborhood around the point 24, okay? And you see the tangent line is really, really close in the magnification to the actual curve itself because you're really close to it. In 2.6.2, well, it's a different figure. I thought that was going to be the same one. Basically, what this gives you is the direction, and that's about it, okay? But if you were to pick some other point a little bit off from X, okay, like X1, well, they come up with this linearization function, and the thing that, yes, sir. At 12 o'clock. At 12, yeah. Okay, are you going to drive separately or drive with us?
I'll probably just follow.
Just follow. Okay, okay. That'll be great. Okay. I guess that I was taking my physical science class too. And he's in it, and he was once on about the field trip. Okay. All right, okay. Now, what we have here is the slope of the tangent line is 1.8, right? We established that. Now, here we have a point, and here we have a slope. We can use the point slope formula, which, by the way, is y minus y1 is equal to m times x minus x1. Sound familiar? Your y1 is your 4, your x1 is 2, and your slope is 1.8. So let's plug that in. That says y minus 4 is equal to 1.8 times x minus 2, right? Okay. This is y minus 4 is equal to 1.8x minus 3.6, right? Okay. Now let's solve for y. In other words, add 4 to both sides. Oops, should write it there, okay? And what does that give us? Y is equal to 1.8x minus, no, plus 0.4. Okay. Okay. And what they call this is the linearization of x. Okay? That's saying, let's follow that tangent line a little ways on x and hoping it's going to stay close enough to the curve. Okay? And as long as you pick an x value that's pretty close to 2, like 2.1 or 1.9 or something like that, you're going to have a fair approximation of what the curve is going to do. Okay? So, that's the linearization of y at x, and it can be used to approximate values of x in a very small neighborhood of 2. Okay? So if you did, let's say, x1 equal to 2.1, we'll plug that in and that'll give you a y1. Okay? If you got a calculator, do you happen to have one? Okay. I have one, but I'd have to get out of this to get to it on my desktop here. Okay, is that easy for you to do? Okay. Because probably relatively easy for me, but I don't want to have to shut down Screencast-O-Matic to get it. Oh, you got it? Okay. So plug in 1.8 times 2.1 plus 0.4. 2.1. Right. Four point what? 3? I couldn't hear you. My hearing's bad. 4.18. Okay, that's what the book got. I was hoping they were right. Okay. 4.18. Okay. Okay. So you went a little ways away from 2, and you went a little bit away from 4 too, and you're going in the right direction. You know, so that gives you. Okay. Well, then what do we do from there? We take that as the new one and plug that back into your y prime, your original function, and you do y prime is equal to f of 2.1, 4.18. Okay, you come up with a new slope, a new linear approximation. Pick another value and just crawl along like that, and and that's how you proceed. To generalize that procedure, just illustrated, we use the linearization of an unknown quantity y of x at 1, of equation 1 at x equal x0, and you come up with that same type form. Now I think I'll clean this because this is going to make the more generic form. If you have some x equal x0 and you have a linear equation, a differential equation, y prime is equal to some f of xy, and you're given some x0 and possibly the y0 as well, in other words, your original form, I wish I hadn't erased it all. Now let me back up and redo. Here's your y prime. Why did I open a parentheses there? I don't need one. Is equal to some function f of xy. Okay? At some initial value, y at x0 is equal to y0. It's a pretty ugly 0, but I hope you can follow what I'm talking about. Okay? You can plug in this value here. So your y prime at x0, y0 would be your f at x0, y0. Okay? that gives you a slope at a point, and then you can do your slope point formula that y minus y0 is equal to that slope, which is f of x0, y0, times x minus x0, and you can proceed from there and make this your linear approximation. The y would be L of x would be y0 plus f of x0, y0 times x minus x0, okay? Your subscripted things are actually values that you were given in the original problem, and your x is the variable here of this linearization, and you can proceed just like we were going on the last one with actual numbers. Now we're just using symbols for it, and that will give you some, then pick some x fairly close to x0, plug that in, you'll get some y fairly close to your y0, and then that gives you a new point, and then you do your y1 is equal to f of x1, y1 times x minus x1, okay? And you can just sort of creep along there and move along that way. The graph of that linearization is a straight line to the graph of y is equal to x at the point x0, y0. If you now let h be a positive increment in the x-axis, along the x-axis, the last time we used a 0.1 was that h. So if you replace your x1, x by x1 is equal to x0 plus h, then this linearization would be L of x is equal to y0 plus f of x0, y0 times, now instead of x, you're going to put in x1, and the x1 is minus x0. This is going to produce some y1, by the way, but that x1 is x0 plus h, okay? So that would be y0 plus f of x0, y0 times x0 plus h minus x0. But look at that, the x0's go out, and so you have y0 plus f of x0, y0 times h, okay? Or move that h in front if you want to. That makes it look a little nicer. That gives you your y1, okay? And then from there, you can do another increment of h and go up from there and keep stepping along. Now, the step size, the phrase is reasonably small. Well, how small is reasonably small? Well, it depends on how much time you got and how far you want to go, but you can proceed with that, and that process is called Euler's method. And the summary of it is y of n minus 1, I'm sorry, n plus 1 it should be, yeah, okay. I was going to say it can't be n minus 1, is equal to y of n plus f of xn, yn times h, okay, where h is that reasonably small step size. And again, they usually write this as y sub n plus h times f of xn, yn, okay? So that gives you your y of n plus 1, okay? And then once you've got a new y of n plus 1, your new x of n plus 1 page. And he just stepped it along in that manner. Okay? That's called Euler's method, which again gives you another possibility of a paper topic. Who in the world was Leonhard Euler? And he, frankly, there have been few people in history who've come up with more things than Leonhard Euler did. You know the basis for our natural number system? E. Guess where that comes from? Euler. He came up with that base. This is an Euler's method of approximating solutions. There's an Euler's equation, there's Euler's formulas, there's Euler's this, that, and the other thing. I mean, he was all over the place, and not just in mathematics. I was thinking Gauss, but Euler was, if I'm not mistaken, he's the one that gave us function notation, f of x. I mean, we sometimes think that was probably someone like Leibniz, but it really wasn't. It was Euler. So he has done incredibly. If my memory's right, there's very few people who have ever published as much as Euler did. I mean, it just, and many of his things were just groundbreaking. If you took the greatest mathematicians of all time, of course, that would have to include Newton and probably maybe Gauss, but definitely Euler. And you'd probably have to go back and find a few others, Euclid and some of the others too, but Archimedes, but he's right up there in the top. Okay. So let's do Euler's method. You've got your sort of calculator form there. So let's do Euler's method for this initial value problem. Oh, wait, I thought it erased it, but it didn't. Okay. Let's try to do it. Y prime is equal to that one we started with, 0.1 square root of y plus 4 plus 0.4 times x squared. Okay? Given the initial condition y of 2 is equal to 4. Okay? It says use Euler's method to obtain an approximation for y of 2.5. So what is your y value when x is 2.5 by using h is equal to 0.1. So you're going to need at least 5 steps or 6 steps to get there. Okay? Then we're going to do it with h equal 0.5. I don't think we'll have time to do that one today because that's going to take 10 or 11 steps to get there. But let's start with what we've got. Okay? Now we already know that. And we know that y prime at that is 1.8. So we can go straight to y of, and we already did this one. Y of 2.1 is equal to 4.18, right? We already did that step, right? Earlier, okay? So let's move on from there. Y of 2.2 would then be 0.1, okay, wait. Okay. Sorry, I was getting a little ahead of myself here. Okay. Euler's method says that, let me write it down here so we'll, y sub n plus 1 is equal to y sub n plus f sub x sub n y sub n. I always forget to put the h there. There. Okay. So, y of n plus 1, which is 2.2 is equal to y sub n, which is 4.18, plus 0.1, that was your step size, times your f of 2.1, 4.18. Okay? Now, what you have to do here is this is your f of x, y. That's what this is. Okay? So, you got a calculator. Now, does that follow a rule of order of operation pretty well, or do you have to watch out for that? Right, that's what I thought. Okay. So, what you do is 4.18 plus 0.1, and do you have to do times, or can you just open a parentheses? Okay, open a parentheses. 0.1 times the square root of 4.18 plus 0.04, open parentheses, 2.1 squared. I don't know if your rule of order of operation does that correctly, but try it.
I don't think you did it right, because I got 4.41.
Okay. Well, it's not far off.
It's not too bad.
Okay. So let's see if we can put in some parentheses better there. That's 4.18 plus 0.1 times 0.1 times, can you do a square root? Just multiply it, write it next to that. Okay. 4.18. What's that?
I just kind of got to work backwards.
Okay. 0.4 times 2.1 squared. Okay, I don't know. I know the little cheap calculator I use sometimes. I have to really watch these things. Yeah, here's where your problems don't rise. If that doesn't follow rules of operation, when you do plus this, it's going to add this to that. Okay. So yeah, you might need another set of parentheses here and there. I don't know. That might work for you. Say again?
I got 4.3. This is
3. They got 4.3768.
Oh, yeah, that's right.
That's it. Okay, yeah. Did that extra parentheses do it for you?
Yes.
Okay, yeah. So this gives you 4.3768. 3768. Okay. Oh, this is going to be so much fun. Y of 2.3 is then going to be 4.3768 plus 0.1, open a parentheses, 0.1 times the square root of 4.3768 plus, open another parentheses, 0.4 times 2.2, that was our previous one, squared, close, close. You get it? Oh, I don't know. Were you doing that too? Okay. This is just punching numbers now.
Yeah.
But that would then give you the next approximation, which would be they got 4.5914. Obviously, they're rounding to 4 digits. You're going to have a lot more digits than that. But hopefully, you'll get close to that. But if I were you, I wouldn't round. I would just take whatever is at the end of there, plug it in here, plus this, times this. Well, here you might have to round to get it there, plus this. That's exactly stuff. And you get another. And supposedly you get from that 4.5914. Okay? And then y of 2.4 would then be that number, 4.5914, plus 0.1 times 0.1 times the square root of 4.5914, plus, open another parenthesis, 0.4 times 2.3 squared, close, equal. And they, what's that?
I got that in the calculator.
You did. Fantastic. Then you do it again, and they say you get 4.82144, 4.8244, and then you plug in one more time to get y 2.5. That's what you're looking for. And that'd be 4.8244 plus 0.1 times 0.1 times the square root of 4.8244 plus, I put in an extra parentheses there. I closed one I shouldn't have. That. Okay. Open 0.4 times 2.4 squared, and they then come up with 5.0768. Now, I wish there were some way I could actually work the problem for you and tell you, now the real answer is blah, blah, but this, the reason we're doing this one is it doesn't have, you don't have an analytical solution, so you can't really say that, okay? But then using h of 0.05, you can't even start there. No, I won't. Okay, we're out of time. But you can play around with that if you want to. I'll mark it. That's where we're going to pick up next time. Boy, that break did help me a lot. I can breathe again. But I did. So we'll look at the H. We won't do all those, but we'll set them up. And if you want to go back and do those again, we'll do that. So anyway, we'll pick up there for next time. I don't know if we got far enough for you to do any new exercises, but guess what? Next time we will finish this chapter, and I'll have the test ready for you next time. Knock on wood. I've got to remember to make that copy. So we'll pick up and go from there next time. If I hadn't had the pause today, we might have finished today. We'll do it next time. Good deal.